This is George Graybill, and I'd like to read to you from the book Stuff, the fortunes, foibles, and fiascos of those who sought to understand matter. This is going to be chapter 11, titled Atomic Models, or Plum Pudding and Planets. You know now that stuff is made of atoms. I hope you didn't think we could quit there. I'm sorry, but you don't ever get to quit in science. When you discover something like atoms, you next have to try to figure out what they are made of. When you've done that, then you have to ask what the things they are made of are made of. Atoms are made of even smaller bits called subatomic particles. If you know about 3 of these bits, you'll see that a lot of the discoveries we have talked about earlier, like the periodic table, will be explained. These 3 sub-bits are called protons, neutrons, and electrons. The electron was discovered by an Englishman named J.J. Thomson. Wish we had J.J. around to explain this next part, because he was one of the best science teachers ever. 8 of his students and his son went on to receive Nobel Prizes in science. Of course, he got one too for discovering the electron. He discovered electrons by fooling around with a cathode ray tube. This gadget gave off a beam of high energy, something or other. Thomson observed that the beam went away from a negative electrical charge and towards a positive electrical charge. This and a few other clues led him to the conclusion that the beam was a stream of negatively charged particles and that they came from atoms. Here is JJ and his amazing cathode ray tube. Atoms do not have a negative charge. They are neutral. So Thomson reasoned that there must also be something in atoms that has a positive charge to balance out the negatively charged electrons. He suggested that the positive charge was spread out over each atom and that the electrons were stuck in it like plums in a plum pudding. I've never seen a plum pudding. Have you? It must be an English thing. Try to picture a chocolate chip cookie instead. Here is the plum pudding model on the left and real plum pudding on the right. Forget the plum pudding model though. It was a start, but not a very good one. It was one of JJ's clever students, Ernest Rutherford, who made the first improvement. Ernie tried passing a stream of positively charged particles through a thin sheet of metal. The results were a surprise. Most of the particles changed directions very slightly, but a few of them went whizzing off at strange angles. Rutherford concluded from this that most of the mass and all of the positive charge was located in the center of an atom. This type of little nut came to be called the nucleus. So these results led Rutherford to claim, I think the plum pudding model is plum loco. Rutherford's model is called the Planetary Model. He imagined electrons traveled around the nucleus in circular orbits, just like planets around the sun. In between the electrons was a lot of empty space. That was closer, but there were problems. Does the Planetary Model remind you of anything? That's right, the old alchemist theme song, as above, so below. Well, in this case, not so much. With the help of others, Rutherford also figured out that the positive charge in the nucleus was divided equally among particles called protons. These protons have a lot more mass than electrons, and an opposite and equal charge. Each atom has the same number of electrons and protons. As we move along a row in the periodic table, each successive element has one more electron and one more proton. The number of protons each atom of an element has is called the element's atomic number. But there was something fishy about the planetary model. Moving charges give off energy. Electrons circling a nucleus is a moving charge. If the electrons were losing energy, they would slow down and crash into the nucleus. They don't. This puzzle was solved by a new approach called quantum mechanics. At the time all this was taking place in the early 1900s, it was finally generally accepted that matter was quantized. In other words, matter comes in separate bits called atoms. A quantum is one bit. More than one bit are quanta. Very few people still thought that matter is continuous, as Aristotle and those guys had thought. On the other hand, most people thought energy was continuous. Then, in 1900, along came a German named Max Karl Ernst Ludwig Planck. Okay, if we just call him Max. In his youth, Max was an accomplished musician, but decided he would rather go into physics. A physics professor, Philip von Jolly, discouraged this idea by telling him physics was a poor choice because everything had already been discovered in that field. Max ignored the advice and became a theoretical physicist. Here is a picture of Albert Einstein on the left, Planck, and someone ordering another round of drinks. There was a law used in those days to predict the amount of energy radiated from a heated object. The law worked well at low frequencies of radiation, but at high frequencies it predicted that an infinite amount of energy would be given off. This impossible result was called the ultraviolet catastrophe. It seems a bit alarmist. Energy doesn't become infinite at high energy, so how can something that never happened be a catastrophe? Planck found a law that worked, which is now called Plancks Law. He tried assuming that the energy given off was quantized. This would mean that energy comes in bits that cannot be split into smaller bits. Based on this idea, he derived the following equation. E equals h nu, where E is energy, h is Planck's constant, and nu is the Greek letter nu, is frequency. The equation worked great. Max got a symbol named after him, and quantum mechanics was off and running. The quantization of energy turned out to be a very big deal. But Planck himself, or is it Planck, I don't know, didn't get too excited about this equation. He thought of h as just a sort of fudge factor he threw in to make the math match the experimental results. He wasn't convinced that energy was really quantized. A few years later, Albert Einstein took the idea of energy quanta and used it to explain the photoelectric effect. This effect happens when some materials are hit with certain frequencies of light and kick out an electron. This can't be explained if it is assumed that light is a wave. Albert showed that it can be explained if light comes in little packets of energy, that is, quanta. These packets later came to be called photons. So sometimes light acts like a wave and sometimes it acts like a stream of particles. Scientists were asked to believe that two things that can't both be true at the same time can each be true at different times. Understandably, not everyone was buying this. We will look into this disturbing puzzle in the next chapter along with other weirdness. Now everything was in place for the next new atomic model. First, we have to talk about spectra. When light or other radiation is shined on atoms, they can absorb some of it. The row of wavelengths they absorb is called the absorption spectrum. When atoms give off light, it is called an emission spectrum. The strange thing is that these spectra show very sharp lines that represent only certain wavelengths. This leads to the conclusion that if electrons are zipping around in circular paths, they can only travel at certain distances from the nucleus, but nowhere in between. That seems odd. And here are the emission and absorption spectra of the element helium. Yet another former student of Thomson's, Niels Bohr, came up with the atomic model that explains these spectra. Today we call it the Bohr Model. Niels heard about quantized light and wondered if maybe electron energy levels were also quantized. This would be a useful modification of the planetary model, Niels thought. The Bohr model is based on this idea. Electrons can have only certain energy levels, but they can move from one to another. An electron can move up to a higher energy level by absorbing an amount of energy equal to the difference between the levels. If it drops back down, it gives off the same amount of energy. In other words, the jump shows up as a line on the spectrum. The Bohr model shows that electrons don't lose energy and crash into the nucleus because they are stuck in various energy levels. But it doesn't explain why. Do you have anything that glows in the dark? These things are said to be phosphorescent. When the lights are on, it kicks electrons up to a higher energy level. They glow in the dark because the electrons are one by one returning to their original level. A material that glows with a new color when light is shined on it is said to be fluorescent. This is more spectacular, and it appears as soon as the light hits it. To see fluorescence, all you need is a little ultraviolet flashlight, which doesn't cost much. Now go outside at night and shine the light on some rocks, looking for the ones that change color. Here's an example. This is the same rock. On the left, it has regular daylight shining on it. And on the right, it has ultraviolet light shining on it. First, you see the effect of daylight, and then you see the effect of ultraviolet light. If you can't find any rocks that work where you live, try a rock shop or the gift shop at a national or state park. Look for rocks that fluoresce and buy the ones with the wildest color changes. Are you back? Did it work? The picture of the electron energy levels of atoms was beginning to become clear. Atoms with certain numbers of electrons behaved differently from atoms with other numbers of electrons. There is a pattern to the way in which atoms of different elements form compounds. That pattern depends on the energy levels of the outer electrons. One way to display this pattern is the periodic table. If only Dmitri could have been there. It was becoming more and more clear that the periodic table was actually a diagram of the electron energy levels of atoms of all the elements. This next part can take you a very long way toward understanding chemistry, but you'll have to pay attention. Electrons surround an atom and occupy different energy levels. The highest outer level is important because these are the electrons that are involved in chemical reactions. The outer electrons are also called outer shells. Outer electrons of two atoms combine to form a chemical bond. When electrons form a bond, they drop to a lower level and give off energy. This energy is often in the form of light and heat. And here is a chemical reaction giving off light energy and heat energy. When an atom has either 2 or 8 electrons in its outer level, it is very stable. In other words, it doesn't tend to form bonds. It is unreactive. It is inert. 2 is the magic number for the first row of the periodic table, and 8 is the magic number for the other rows. Hydrogen atoms have 1 electron, and helium atoms have 2. 2 hydrogen atoms bond together to form a hydrogen molecule with the formula H2. Now, they are stable like helium because they have completed their outer shell by sharing electrons. Is there a moral lesson here about sharing? All across the periodic table, atoms of each element form bonds by losing, gaining, or sharing electrons to end up with an outer shell of 2 or 8 electrons. All the elements in each column of the periodic table react in the same way because they have the same number of outer electrons. Look at the periodic table. In the first column, hydrogen, lithium, sodium, potassium, etc. all have 1 outer electron. In the 7th column, fluorine, chlorine, bromine, and iodine, and so forth, all have 7 electrons. Elements in the first column give an electron to elements in the 7th column, and then they both have a complete outer shell. This is the periodic table used today. That last bit was a big chunk of the heart and soul of chemistry as it is understood today. Are you ready for more? That was plain old everyday chemistry, but have you heard of nuclear chemistry? In chemical reactions, new materials are formed by rearranging atoms, but the atoms don't change. In a nuclear reaction, new elements are formed by rearranging particles in the nucleus. Remember how alchemists tried to change one element into another? The problem was they didn't have nearly enough lab equipment. To understand how nuclear reactions happen, you first need to know about a third subatomic particle, the neutron. This one was very hard to find because it has no charge. It doesn't give itself away as it passes by a magnet or an electrical charge. It wasn't until 1932 that the neutron was discovered by yet another Englishman, James Chadwick. Even though he wasn't a former student of JJ's, he still got the Nobel Prize for his discovery. Find a particle, win a prize, seems to be the rule. Adding neutrons to the list of things in an atom explains a lot. A neutron has about as much mass as a proton. They are found in the nucleus and account for most of the mass that isn't either protons or electrons. They explain why 2 atoms of the same element have different masses. Atoms that have different numbers of neutrons but the same number of protons and electrons are still the same element. Such atoms are called isotopes of an element. Isotopes aren't a special kind of atom. All atoms are an isotope, and all elements have several isotopes. A lot of people don't seem to get this. But here's the thing about some isotopes that changed the history of the world. Many isotopes are not stable. This means that the nucleus breaks apart to form new elements with a smaller nuclei. 1 nucleus, 2 nuclei. This is one kind of nuclear reaction called a fission reaction. Some of these reactions provide the energy released in nuclear power plants and atom bombs. And it is a lot of energy. Long before anyone made a nuclear bomb or power plant, there was a man who knew it was possible. You can probably guess who. Right, it was good old Albert Einstein. When you're asked on a test who made some important discovery about physics, just say Einstein, you'll probably be right. The energy released in a nuclear reaction is summed up by Albert's famous equation E equals mc squared, where E is energy, m is mass, that is stuff, and c is the speed of light, which is a very big number. The little 2 means it is not just c, but c times c. So in a nuclear reaction, some of the mass gets turned directly into an enormous amount of energy. It is so much more energy than you can get from a chemical reaction that it makes your head spin. During World War II, Einstein told Franklin Roosevelt, the President of the United States, something like, "You know, Frank, you could make an atom bomb to get this war over with. If the enemy makes one first, we will be goners." Later, he had second thoughts about this because he knew how terrible dropping an atom bomb on people would be. So the USA made 2 atom bombs and dropped them on 2 enemy cities, and the war was over. Those 2 explosions were just awful. Here is an atom bomb scaring the pants off us. When Einstein heard the news that the first bomb had been dropped, all he could do was sit there saying over and over again, "Oy vey, oy vey, oy vey." Oy vey is Jewish slang for alas, or woe is me. And that is the end of chapter 11. If you scroll down below the YouTube video, you'll see a link to where you can buy the book, read reviews of the book, look inside the book, and things like that. Also, if you look down in the corner of the video screen, you'll see a button that says subscribe, where you can subscribe to my YouTube channel. And the next chapter I'll read will be chapter 12, titled Deeper into the Atom, or How Can You Be in 2 Places at Once When You're Not Anywhere at All? Goodbye, I'll see you next time.